Okay, for question 9, we have a BJT with beta equals 50 and an early voltage of 120 volts when measured at room temperature, and the base current is 40 microamperes. So for A, we have to draw the hybrid pi equivalent circuit of the BJT showing the relevant parameters, and then compute the corresponding small signal parameters. And for B, we have to draw the T equivalent circuit and then calculate the small signal parameters. So for the drawings of the hybrid pi and draw in the T equivalent circuit, uh, I advise you to go over the solution sheet on CU Learn, so you can see that. You can see there the circuit itself. But for part A, for the hybrid pi model, we need to determine the output resistance, which is the early voltage divided by the collector current. Okay. Now for the collector current, we know that this is beta times IB, and in our case, it's 2 milliamperes. So this gives us 120 divided by 2 milliamperes. That's equals to 60K ohms for the output resistance. Then the transconductance Gm is equals to the collector current. Now we are at room temperature, so Vt is 25 millivolts. So this is 22 milliamperes divided by 25 millivolts. That's equals to 0.08 ampere per volt, right? And then for our pi, that's for the hybrid pi model, we have that beta over Gm, and that's equals also to Vt divided by the base current, which in our case is equals to 625 ohms. Okay, now for part B, we need to determine again the output resistance. That's the same as the previous one, so it's just 60K ohm. We also have to determine the transconductance. That's the same as the previous one. Okay, but now for the T model, we have to calculate the emitter resistance, the small signal resistance, which is alpha over Gm, or the thermal voltage Vt divided by the emitter current. And this gives us 12.25 ohms. Okay, so that's it for this problem.